Let's take a calm, mechanistic look at the hidden structural forces that drive complex systems. In this explainer, we're going to uncover exactly why systems designed to share resources eventually and quite inevitably turn on themselves. We're examining the underlying architecture of failure.
There's this super common belief we all hold when designing systems. We assume that sharing resources maximizes efficiency. We pool our resources, we consolidate distribution centers, we merge our digital pathways. It just feels like the right thing to do, doesn't it? But we have to contradict that assumption right out of the gate. Maximizing shared utilization actually, mathematically, guarantees systemic gridlock and eventual failure. To understand how this actually happens in practice, let's look at a really simple, tangible piece of infrastructure. Imagine a single main water pipe that branches out into 3 distinct, independently operated local valves. Each valve is controlled by a totally separate operator, and their only job? To ensure their specific local reservoir gets a steady, constant supply of water from that main pipe.
So, let's start the system up. Initially, everything is perfectly balanced. The main pipe is delivering exactly 100 units of water per minute, and the 3 valves are drawing exactly 100 units combined. Flow is operating at its theoretical maximum efficiency. Everyone gets exactly what they need right when they need it. The system is quiet, predictable, and flowless. But this kind of perfection, it's incredibly fragile. Section 1. The physical constraint.
Now we're going to observe what happens when random, completely unavoidable fluctuations disrupt this perfect equilibrium. Because in the real world, arrival rates and departure rates are never perfectly static, are they? A slight surge in demand or a momentary delay in supply is going to happen in any dynamic environment. When a momentary fluctuation hits, the input volume briefly exceeds the available capacity of the main pipe. And since the pipe is already running at 100%, it has absolutely no slack, zero. It cannot absorb the surge. So a physical accumulation begins. The water can't simply pass through anymore. It has to wait. And this temporary accumulation rapidly transforms into a permanent state. The drop in throughput forces the fluid into a waiting state, which creates a structural delay. Because the system literally has no excess capacity to process this backlog, the queue just persists. It immediately starts degrading the entire process chain. That physical line of waiting material begins stretching backwards, slowing down absolutely everything behind it. Section 2. Rational escalation. This physical delay triggers a highly specific response. Let's shift our focus away from the main pipe and down to the localized response at those 3 reservoir valves. Remember, these operators are entirely blind to the overall system. They only monitor their own local flow. Right now, because of that upstream queue we just talked about, they sense their flow decreasing. What happens next is a perfectly rational local action. To maintain their individual throughput, every single valve operator decides to open their valve just a little bit wider. They're just trying to pull their required volume out of a diminishing stream. In a corporate setting, this is exactly like a department hoarding its budget, or a software program aggressively requesting more processing power the second it detects a lag. It is a strictly logical decision based entirely on local information. But here is exactly where the contradiction takes hold. As one valve opens wider to capture more flow, it alters the physics of the entire pipe. One valve's maximum utilization literally forces the others to operate at a lower capacity. The other 2 operators see their flow drop even further, so naturally, they respond in kind. They open their valves to the maximum. By trying to maintain their own output, they collectively shrink the overall output of the entire network. The resulting disparity here is severe. The physical constraint of the main pipe, the system capacity, remains entirely fixed. It cannot grow. But the localized demand has artificially spiked because every single valve is now demanding maximum draw simultaneously. Individual demands now mathematically exceed the strict physical limits of the system. The tension is escalating rapidly, and the system is effectively beginning to tear itself apart. Section 3. The hidden architecture. We really need to look beneath these physical symptoms now and ask why the system actually encourages this destructive behavior. The answer doesn't lie in a mechanical flaw, but in how the costs and benefits are distributed across the shared architecture. The absolutely crucial point is this. Each local valve receives the full immediate benefit of opening wider. If they get a single drop more water, they win. But the penalty for that action, the overall drop in pipe pressure, is not felt by that individual valve alone. The pressure drop is distributed blindly across the whole system. The local benefit is highly concentrated, but the systemic cost is completely diluted.
We've now reached a state known as resource contention. Notice that the physical bottleneck itself did not cause the system to fail. The failure was created by the simultaneous, uncoordinated competition for that bottleneck. When multiple independent processes demand access to a shared resource that just cannot serve them all at once, they stop performing productive work. Instead, they expend all their energy simply fighting for access.
This dynamic organically incentivizes total depletion. There is no single valve that has a structural reason to reduce its draw. Think about it. If one operator decides to be responsible and close their valve just a bit to let pressure rebuild, the other two fully open valves will instantly consume that water. The responsible operator gets absolutely nothing. Therefore, the system's structure heavily penalizes cooperation and actively rewards maximum aggressive extraction.
Section 4. Irreversible lock-in.
Let's return to our physical water pipe to observe the ultimate result of this intense contention. The escalation has reached its absolute peak. The intense, simultaneous draw from all three fully opened valves has exhausted the throughput entirely. The pipe pressure collapses. The network is now expending all of its structural energy simply managing the conflict between the valves, rather than moving any actual fluid. The system is working incredibly hard, but producing absolutely nothing. At this point, the system is completely deadlocked, and the valves remain stuck in the fully open position. Closing a valve now means surrendering access entirely, so no local operator can rationally shut their valve. The structural logic of the system has trapped them. Even though keeping the valves open guarantees that no water flows for anyone, it is still the only mathematically rational choice available to the local operator. They're totally locked in.
We've hit rock bottom. The flow rate reaches absolute zero. All resources are entirely wasted, either waiting in the queue or expended in the endless loop of contention. The very system that was designed to share a resource with perfect 100% efficiency has mathematically guaranteed its own total paralysis.
Section 5. Structural destiny. It's so tempting to look at our frozen pipe and try to find a quick solution, a way to just fix the flow. You might be thinking, hey, let's just make the main pipe bigger, or let's add a massive buffer tank upstream. But a purely mechanistic view requires us to see that merely expanding the pipe or adding a buffer doesn't eliminate the structure of contention at all. It simply shifts the bottleneck. It relocates the failure further downstream. That new, wider pipe will just feed an even larger system, generating a much more massive and catastrophic gridlock when the inevitable fluctuation hits again. We have to realize that there were no errors here. There were no villains, no bad actors, no malicious intent whatsoever. Every local component, every single valve operator, executed its function perfectly and rationally based on the limited information it had. But because the architecture rewarded local consumption while sharing global costs, local optimization mathematically guaranteed global system failure. I want to leave you with this final, irreversible realization. When you look at congested highways, collapsed supply chains, or frozen computer networks, you are not watching a breakdown. You are watching a system functioning exactly as it was designed to. Complex shared architectures are destined by their mathematical nature to reach gridlock. The system didn't fail. It followed its structure.